We talked about four main terms yesterday. First term was electric potential energy. The second term was potential energy difference. Can't spell this morning. Potential energy difference. The third term was electric potential. And then the fourth term was electric potential difference. So four terms, all sounding very much alike, but all slightly different from one another in terms of what they actually mean. Potential energy, if you remember, we said, is the amount of energy that's stored in a system of two charges a certain distance apart. When you bring two charges, a positive and a positive, a negative and a negative, a positive and a negative, a certain distance apart, there is a force of attraction or repulsion. Therefore, there is a certain amount of potential energy. The energy stored in that system of those two charges, that certain distance apart, is the potential energy. The symbol we give to that is E, just like it was for gravitational potential energy. Now, the potential energy difference is just simply the difference in the amount of electric potential energy. So we've got two charges. In this situation, we've got a certain amount of electric potential energy. When we move them closer together or further apart, we've got a different amount of potential energy. The potential energy difference is the difference in energy between those two situations. Now, the potential energy difference, the change in potential energy, can also be known as what variable? There's another word that we use to describe the potential energy difference or the change in electric potential energy. What is it? Work, yeah. So delta EP, the change in electric potential energy, is also equal to the work. The work can also be equal to F times D. Be careful with this one, though. That delta D is the displacement of the charge, the amount that the charge has moved, as opposed to, say, the distance between the plates. So if you've got a situation where you've got a charge in between two plates, the distance between the plates can be used to find the electric field, but not to find the work. For the work, you have to use the displacement of the charge, how far the charge has actually moved. Now, electric potential, on the other hand, the only thing we're doing here with the third term is changing the first term by dropping the E, dropping the energy. So we've got electric potential as opposed to electric potential energy. It is the amount of energy per unit charge. So if we have 10 people and $100, $100 would be analogous to the potential energy. $10 would be analogous to the potential, the energy per person, or the money per person. The electric potential energy per unit charge is equal to the electric potential, and the symbol for that is V, capital V. And of course, since it's the energy per unit charge, it's going to be E over Q. Tell me what the units for electric potential would be. There's two sets of units that we can use. One is kind of staring you in the face. Both of them are actually staring you in the face. One from the equation, and one slightly different. What units do we get from this equation if you look at E over Q? Joules per coulomb, right. And a joule per coulomb is also equal to 1 volt. So 1 volt, 1 capital V, is the unit for potential, which the symbol for that is also V. Potential difference? Well, potential difference is just the difference in electric potential between two spots, or the difference in the amount of energy per unit charge. There's two ways we can find delta V, the change in electric potential, or the potential difference. The most obvious way is to say it's the final minus the initial. Delta anything is final anything minus initial anything. But we can also say not E over Q, but rather delta E over Q. So it's the change in energy per unit charge between two spots. The units for that would also be joules per coulomb or volts. Finally, we learned one new term yesterday, which was another unit for energy. And that term was the electron volt, or 1 electron volt, meaning the amount of energy that's gained or lost by an electron as it accelerates through a potential difference of 1 volt. As it moves through a potential difference of 1 volt, depending upon which way it's going, it can either gain 1 electron volt of energy, or it can lose 1 electron volt of energy. 1 electron volt ends up being equal to 1.6 times 10 to the minus 19 joules. That's how much energy in joules an electron would gain or lose as it went through a potential difference of 1 volt. So therefore, we're going to define that as being 1 electron volt. You got to do conversions here. Convert from electron volts to joules. Let's set up a ratio. 1 electron volt over 1.6 times 10 to the minus 19 joules equals, well, depends on what you're solving for here. If you're looking for the number of electron volts, then you're going to put the x on the top. Okay, x electron volts over however many joules you have. If you're looking for the number of joules, given the number of electron volts, then you're going to put the x on the bottom. Say 1 electron volt over 1.6 is equal to however many electron volts you have over x joules. Just solve for x. Okay, that's the easiest way to always do that unit conversion from electron volts to joules or joules to electron volts correctly. And you will have to do that. Okay, I promise you'll have to do that. All right. Let's do an example problem that we didn't quite get to yesterday, 11.7 on page 565. Moving small charge, 1.6 times 10 to the minus 19 between two parallel plates increases its potential energy by 3.2 times 10 to the negative 16 joules. What's the potential difference between the two plates? If you remember and understand all of those terms that we've just reviewed, then this is not a hard question. But it is a little bit tricky, a little bit tough to remember, at least right now, all four of those terms, because they're so similar in terms of the language, but yet just a little bit different in terms of what they actually mean. What do we have here? This is going to be a charge, right? 1.6 times 10 to the minus 19 coulombs. Increases its electric potential energy by this much. What variable are we going to call that? Is that electric potential energy? Not quite. It's the change in electric potential energy. It's delta. It's delta EP. And we're looking for the potential difference. We're not looking for V. That's potential. We're looking for delta V, the potential difference. Now, we've got a couple of options to find potential difference here. We can say VF minus VI, the final minus the initial potential. Or we can say delta V is equal to delta E over Q. I think it's pretty obvious which one we're going to use here. We've got delta E, we've got Q. Let's say delta V is equal to delta E over Q. That's going to be 3.2 times 10 to the minus 16 joules. That's our total amount of change of energy, divided by the amount of charge we have. And that's going to give us the amount of energy per coulomb that was gained or lost, the electric potential difference. 3.2 divided by 1.6 is 2. This should have been 10 to the minus 16 on the top. That's going to be 10 to the 3, 10 to the positive 3. And that's going to be joules per coulomb, or what's the other set of units we can use? Volts, right? 2.30 times 10 to the 3 joules per coulomb, or 2,000 volts. As I say, guys, that's not a hard question if you remember all these terms and you understand all these terms and you get your variables correct, your givens correct, right? If you start calling 3.2 times 10 to the minus 16 delta V, because, I mean, the term is almost the same, right? Potential difference, potential energy difference. If you start calling it the wrong variable, then you're not going to get this question right. But as long as we get that straight, the givens straight, we should be good here. Should be good for this one, and we should be good for these ones on page 565. All right, if we have no problems with those questions, let's move on to one more example on this topic. 566. This one looks a little bit tougher. We get this diagram that's a bit confusing here. It says a small charge of 3.2 times 10 to the minus 19 coulombs is moved between two parallel plates from position with an electric potential of 2,000 volts to another position with an electric potential of 4,000 volts. And we don't seem to be asked a question here. I must have only copied over part of the question. Somebody want to real quickly just check the book on 566 and see what we're actually being asked for this question, please? Thank you, Joel. We're looking for two things here. We're looking for the potential difference. In question A, we're looking for the potential difference. And in question B, we're looking for the electric potential energy gained And we're looking for that potential energy gained in joules and in electron volts. All right, let's circle some givens here first. We don't have any kind of crazy units to worry about here. We got coulombs, we got volts, all standard units, so we don't need to circle anything in red here. We will, though, circle this in blue and write down a Q beside it because that's the charge. 2.0 times 10 to the 3 volts, 4.0 times 10 to the 3 volts. What does that mean? What's this number right here, this 2,000 volts, Joel? The initial what? Good. It's the initial V. It's the initial potential. It is not potential difference. It is not an initial potential energy. It is the initial electric potential. Again, there's those 4 terms: electric potential energy difference, potential, and potential difference. None of them are hard, but when we start trying to do questions that involve more than one of them, it gets a little bit confusing. You got to keep that straight. That's the initial potential. This one, therefore, is going to be the final potential, VF. We're looking for the potential difference. What symbol is that, potential difference? Potential energy difference would be delta E. Potential difference would be delta V. So let's find delta V here. How are we going to find delta V? We've got 2 equations that allow us to find delta V. There's VF minus VI, and there's delta E over Q. Which one are we going to use here? Probably VF minus VI, right? That's the easiest way to do it. Now, by the way, VF minus VI isn't on your data sheet for potential difference, but I don't think that's a big deal. VF minus VI is intuitive if we're looking for delta V, right? Delta anything is final minus initial. So we're going to say VF minus VI. It's 4,000 volts. Subtract 2,000 volts. That's going to give me a potential difference of 2.00 times 10 to the 3 volts. I should say 2.0 times 10 to the 3 volts. 2,000 volts. So there's the answer to question A. Okay? Relatively straightforward, again, if you can keep those terms straight. Question B. The electric potential energy gained. What variable are we looking for here? I mean, obviously, electric potential energy gained, right? But what symbol are we looking for here? We're looking for joules, yes. What's the symbol? Not the units, the symbol. What is it? Good. We're looking for delta EP, or the work, right? So what's the change in potential energy, the potential energy gained here? Any ideas as to how we might find that? If we had the initial and the final, we just subtract them, right? But we don't. So we've got to have some other way of finding the potential energy gained. Good. Let's say delta V is equal to delta E over Q. That's valid, right? Potential difference is potential energy difference divided by charge. Let's rearrange that and solve for delta E. We get Q times the potential difference. Now, we've already solved for the potential difference. It's 2,000 volts. The charge is 3.2 times 10 to the minus 19. We multiply those together, we end up getting 6.4 times 10 to the minus 16, I think. 6.4 times 10 to the minus 16. What would the units for that be? Joules, right. When we use standard units in an equation, we get standard units out of it. When we're using coulombs and volts, we're going to get joules. Now, we're also asked for that potential energy gained in electron volts. This is the first time we've had to do that conversion here. Oops, looks like I already had it from the last time. Let me erase that. Remember what we do? We say 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. You don't have to remember that number, that conversion. That's on your data sheet. If you look at the left-hand side of your data sheet, it specifically tells you that 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. We're looking for the number of electron volts that's equal to 6.4 times 10 to the minus 16 joules. So we'll put the x on the top. Now we've got to solve for x. The 6.4 goes up by multiplying. So we end up dividing 6.4 times 10 to the minus 16 by 1.6 times 10 to the minus 19. And I think we end up getting 4.0 times 10 to the 3. Is that right? 4,000? The number of electron volts, just a little check for you when you do that conversion. The number of electron volts will always be much bigger than the number of joules. So you're going to always end up with a smaller number for joules and bigger number for electron volts. Right? Obviously, there's quite a bit more to this question than there was the last example question and the practice problems that you were working on. But again, if you keep those terms straight, those four terms, electric potential energy difference, electric potential, and potential difference, then we can do this question. It's not that bad. If you get them mixed up, then you're going to have a challenge here. Okay? All right, a couple questions to go with that one as well. I'll make this a little bit bigger because I think it looks a little bit small for the people in the back corner there. Okay, we'll give you 5 minutes or so to see what you can do with these. Let's take a look at question number 2 here. It says an electron moves between two positions with a potential difference of 4 times 10 to the 4 volts. What's the electric potential energy gained by the electron in joules and in electron volts? No strange units here. There is the whole electron volt thing that's kind of strange, but that's an answer. So we won't worry about circling that in red necessarily. Okay. We'll wait till we get our answer, and then we'll worry about doing that conversion. We got something here given to us. This 4 times 10 to the 4 volts. Tell me what that is. It could be E. It could be delta E. It could be V, or it could be delta V. What is it? The potential difference. It's delta V, right. We've got the potential difference is 4 times 10 to the 4 volts. We're looking for the potential, the electric potential energy gained. Is that going to be, it's not going to be delta V, obviously, right? It's going to be V, E, or delta E. So there's only 3 more things it could be, V, E, or delta E. Which one is it? Potential energy gained. Delta E, that's the change in potential energy, right? It doesn't look like we have enough information here. We're missing something. Let's go back and reread this. Okay, if we spot this as soon as we're reading it, then it's probably not a bad idea to make a note of it. I didn't spot that. That's okay. That happens sometimes, right? When we read through something and we don't spot some little trick that's going to help us until later on. Okay, we want to spot it right away. Sometimes we're not going to. What is it that I'm missing here? What is it that I really needed to draw attention to at the very beginning of the question, Jade? Yeah, we've got the electron charge. We've also got the mass of the electron as well if we need it, although in these questions we don't seem to need it. So we've got the charge. It's on our data sheet. We've got the potential difference. We're looking for the change in energy. Let's use delta V is equal to delta E over Q and rearrange that equation. Delta E is equal to Q times V. Q is 1.6 times 10 to the minus 19. It's actually negative, but we're going to drop the sign of the charge as we always do when we're plugging it into an equation. We'll multiply that by the potential difference of 4 times 10 to the 4 volts. That's going to give me 6.4 times 10 to the negative 15. And what would the units for that be? What would the units for that one be? We use standard units here, right? We used coulombs and we used volts. So the standard unit for energy is going to be joules. So our answer would be 6.4 times 10 to the negative 15 joules. Now, we also have to convert that to electron volts. Remember the conversion? We say 1 electron volt equals 1.6 times 10 to the minus 19 joules. Whichever way we're converting, we always start this way. Now we're looking for the number of electron volts, so we'll put an X on the top. We've got 6.4 times 10 to the minus 15 joules. Take the 6.4 up by multiplying. Then we're going to see 6.4 divided by 1.6 ends up giving me 4.00 times 10 to the 4 electron volts. Notice in this case, the number of the electron volts is exactly the same as the potential difference. Is that a coincidence? Kind of, but not entirely. If we're dealing with an electron or a proton that has a charge of 1.6 times 10 to the minus 19, the potential difference will be the same as the number of electron volts, even though it means two different things. But if we're dealing with an alpha particle or something that has a charge other than 1.6, then the potential difference won't be the same as the number of electron volts. So I would caution against just remembering that the potential difference is going to be the same as the electron volts. That works if we're dealing with an electron or proton, but not if we're dealing with something that doesn't have that charge. I'd go through that process each time, just to make sure. Okay? I'm going to draw a picture here that's going to look like it has nothing to do with electricity, but bear with me for just a second, okay? We're going to draw a connection between energy, electric energy, and gravitational energy again. This whole unit has been drawing that connection between gravity and electricity, right? There's so many different things that are similar between gravity and electricity. We got a car at the top of a hill here. Let's say that car, let's say it's a go-kart, so it doesn't have an engine, it just coasts, right? It has an initial velocity, let's say, of 0 meters per second. Let's say the height of this hill is, let's say it's 10 meters. Okay, and that car is going to go down the hill. We'll call that initial spot, we'll call it the initial spot, and we'll call this our final position down here at the bottom. If we wanted to find the speed of this car at the bottom of this hill, what would we do? What concept would we use to find the speed of this car at the bottom of the hill? It's a pretty straightforward question, actually. A question that you saw in Physics 20 in practice questions and assignments. You saw it in unit tests. You saw it in final exam. You've seen questions like this before. What do we do? Somebody said it. I heard somebody say it. Conservation of energy. We're going to say EI is equal to EF. Right? Initial energy is equal to the final energy. Now, ask yourself a couple of questions at the top and the bottom. What kind of energy do we have at the top of this hill? Do we have kinetic energy at the top of this hill? No, because it's not moving, right? Do we have potential energy at the top of this hill? Yes, we do. What kind of potential energy do we have at the top of the hill? Gravitational potential energy. So we're going to say EI is mgh. We could say it's kinetic plus potential and then just cross off the kinetic if we want, or we could just drop the kinetic to begin with and say it's just potential. What kind of energy do we have when we reach the bottom of the hill? Do we have kinetic energy when we reach the bottom of the hill? Yes, because it's moving, right? So it's 1/2 mvf squared. Do we have potential when we reach the bottom of the hill? No, we don't, because there's no height. So we're just going to leave it at that. We could say 1/2 mv squared plus mgh if we want, and then cross off the mgh, but we don't really need to do that because we've only got the kinetic energy. Is that okay? What does that have to do with electricity? Well, let's now take two parallel plates. Let's say the top plate is positively charged and the bottom plate is negatively charged. And let's say we've got a positive charge right at the top plate with a speed of 0 meters per second. It's going to go down here to the final position at the negative plate. We're going to analyze this question in the same way as we just analyzed the last question. We're going to say EI is equal to EF. You got to ask yourself a couple of questions at the top here, or when it starts. Do we have kinetic energy? We don't know much about this kind of question yet, but we do know whether it has kinetic energy or not. What's the answer to that question? Does that positive particle have kinetic energy when it's at the positive plate? No. Why not, Jordan? Because it's not moving. And we're told that it has a speed of 0 meters per second, so it has no kinetic energy. Does it have potential energy at the top? Yes, it does. Something is going to cause it to go down to the bottom plate. It's got potential energy. Now, here's the trick. It's not gravitational potential energy anymore, is it? What kind of energy is it? Electric potential energy. Now, what's our equation for electric potential energy? We said that electric potential is the amount of energy per coulomb of charge, so the energy would be equal to the charge times the amount of electric potential. So let's say electric potential is not mgh, but rather it's QV. The initial energy is still potential as it was in this Hill question, but it's not gravitational potential, it's electric potential, QV. What kind of energy does this charge have when it reaches the bottom plate, or this negative plate? Does it have kinetic energy when it reaches that plate? Is it going to be moving, Courtney? Yes. It's moving, so it's got kinetic energy. Does it have potential energy when it reaches the bottom plate? Does it have any more potential to go somewhere? No. It's like the car has reached the bottom of the hill. So it doesn't have potential energy. Okay, we're going to do a few more things with this in just a second, but what I want you to realize right now is that we're going to see questions where charged particles are speeding up and charged particles are slowing down. As soon as you see that question, as soon as you see a charged particle is speeding up or slowing down, right away I want you to think conservation of energy, and I want you to picture it as a car going down a hill or up a hill. We can do that, right? We can solve this problem easily. This problem tends to be a little bit harder for us because we have a harder time visualizing charges moving than we do cars moving up and down hills. But if we picture this charge as a car going up or down a hill, then we may have a little bit of an easier time dealing with it. So as soon as you see that charged particle speeding up, think, oh, that's like a car going down the hill. What kind of energy would I have at the top of the hill? What kind of energy would I have at the bottom of the hill? Let's change this around a little bit. Let's say this car now has an initial speed of 10 meters per second. What kind of energy do we have at the start of the problem now? Do we still have potential? We do, yeah, because there's still a height, right? Do we have kinetic energy now? We do, because it's got a speed as well. So it's not going to be just potential energy. It's going to be potential and kinetic energy at the beginning of this problem. At the end of the problem, is it moving? So it's got kinetic, right? Does it have a height? So there's no potential. The end of the problem is still exactly the same as it was before. The beginning of the problem is now a little bit different because we not only have a height, but we've also got a speed. We've got potential energy and kinetic energy. Well, let's change this question around a little bit. Instead of this charge being at rest, let's say this charge is moving at 1 times 10 to the 3 meters per second, 1,000 meters per second. Do we still have potential energy at the beginning here? We do, right? We do. It doesn't have a height, but this charge has the ability to speed up. It's a positive at a positive plate. It's going to be repelled by the positive plate, so it's going to speed up just as the car speeds up as it goes down the hill. Picture this as a car going down the hill. A car that has potential energy because it's at the top of the hill, and a car that has kinetic energy because it's moving. The only difference is the potential energy is QV instead of mgh. When the car reaches the bottom of the hill, it has just kinetic. When this charge reaches the negative plate, it has just kinetic energy. What about this one? Let's change this around now so that we're looking for the speed of the car halfway down the hill. That's our final point now. Do we have kinetic energy at the beginning of this problem? Yes. Do we have potential energy at the beginning of this problem? Yes. Do we have kinetic energy at the end of this problem? Yes, because it's moving, right? Do we have potential energy at the end of this problem? Yes, because it's got a height. What would be the initial height there? What would be hi in this problem? 10. What would be hf, assuming we were trying to find the speed halfway down? 5, right? Good? All right, let's change this problem now so that we're not looking for the speed of this particle when it reaches the negative plate, but rather when it goes halfway across. Do we have potential at the beginning? Sure. Do we have kinetic at the beginning? Sure. Just like we did with the car at the top of the hill that was moving. Do we have kinetic halfway through? Is this charge moving? Yes. Do we have potential halfway through? Yes, it's like the car halfway down the hill. If we had potential for the car halfway down the hill, then we've got potential for the charge halfway across the gap here. What's the initial potential there? We don't actually know. Let's say the potential difference across this is, let's say, 100 volts. What's the initial potential in that problem? 100 volts. What would be the final potential in this problem? Sorry? No, the final wouldn't be 100. The final would be 50. Potential is analogous to height here. If we start off at 100 and we go halfway across, then the new potential would only be 50 volts. So if we're cutting the height in half, we're going to cut the potential in half. One more before we actually do a problem here. Let's say now, let me just create a new page actually. Let's say now the car is at the bottom of the hill and it's moving at 20 meters per second. Okay, we want to find out how fast this car is moving at the top of the hill. EI is equal to EF, of course. What kind of energy do we have at the bottom of the hill at the initial point? Is there kinetic? It's moving, right? Is there potential at the bottom of the hill? No, the only reason it's going to go up the hill is because it has inertia. It's moving, right? But it doesn't have any potential energy at the beginning of this problem. What about at the end of this problem? Is it moving at the end of this problem? If we're trying to find the speed, presumably it's still moving. So it's going to have kinetic energy. Does it have a height at the end of the problem? It does, Jade, so it's going to have potential energy, mgh final. Let's twist those plates around horizontally. Okay? Let's make this one a negative plate. Let's make this one a positive plate. Let's put a positive particle right there. A positive particle that has an initial speed of 1 times 10 to the 3 meters per second. It's going across that gap. Charged particle is going to do what? Going to speed up or slow down? This positive, is it going to speed up or slow down? It's going to slow down, right? It's attracted back from where it's coming from. It's attracted back to the negative plate and repelled by the positive plate. It's going to slow down. That's like a car going up the hill. Remember in the last problem, we had this charged particle speeding up. That was like a car going down the hill. This time we've got a charged particle slowing down. That's like a car going up the hill. If a car is going up the hill, it starts off with kinetic energy. And that kinetic energy is converted to potential. Now, we're still going to have, presumably, we're still going to have kinetic energy at the end of this problem, just less of it. But we're also going to have potential energy at the end of this problem because some of that initial kinetic was converted to potential. When you see a problem where a charged particle is speeding up, I want you to think, oh, that's like a car going down a hill. When a charged particle is slowing down, I want you to think that's like a car going up the hill. We can all solve these problems. If we can solve these problems, then there's no reason to think that we can't solve the other problems, the electricity problems, because they're the same thing. They're just harder to visualize. So don't try. Don't try to visualize them as charges moving. Try to visualize them as cars moving, because we can do that. The notes that I copied for you are right here. I'm not going to go through those because we've essentially just described what these notes say, just in a bit of a different way. I want to go straight to example 11.10 on 571 and get that done before the end of class so you're able to do that worksheet question for Tuesday. 11.10 on 571 says a pith ball, tiny little ball that it's really, really light. It's a material that comes from the inside of a plant. It's sometimes used in electrostatics experiments. It doesn't really matter what it is. Has a mass of 2.4 times 10 to the negative 4 kilograms with a positive charge, and it's initially at rest at location A. So here's location A, not moving. I'm going to say that it's 0 meters per second at point A. At this location, the charged ball has 3.00 times 10 to the negative 7 joules of electric potential energy. I'm going to write that that's potential energy there. When it's released, the ball accelerates toward the larger charge, towards this negative. At position B, it has 1.5 times 10 to the negative 8 joules of potential energy. We want to find the speed of the pith ball when it reaches position B. Okay, let's ask this question first. Is this charged particle, this positively charged particle, is it speeding up or slowing down? As it goes toward a negative, as this positive goes toward the negative, is it going to speed up or slow down? It's speeding up because it's an attractive force. If it's speeding up, it's like a car doing what? Going up the hill or down the hill? It's like a car going down the hill, right? Go-karts don't speed up when they go up a hill. They speed up when they go down a hill. So let's analyze it as we would a car going down the hill. EI is equal to EF. This car, however, is a charge. It's a charge at rest as opposed to a car at rest. So when we're dealing with it, we're going to make a small change. Instead of being potential energy mgh, it's going to be potential energy q times v. Ask yourself those two questions. Does it have kinetic energy? Does this car that's at rest have kinetic energy at the top of the hill? No. Does this car or charge that's at rest have potential energy at the top of the hill? Yes. Now, normally we'd say that potential energy is Q times VI, but we already actually have the value for it, so we don't even need to sub in that equation. We can just sub in the value. They're giving me a bit of a break in this question. If they didn't give me the value, that's okay. We just sub in QV. That's the equation for potential electric potential energy. But of course, we need to be given more information if we had to put in that equation. At point B, this is partway down the hill. The car is partway down the hill now. Picture this car halfway down the hill. Jack, what's the color of the car? Yeah. Picture it. What's the color of the car in your mind right now? Green? Right? What kind of car is it? Brenda, what kind of car is it? Is it a big car or a little car? Little car? Is it like a newer little car or an older little car? Nick? Newer one? Okay. Picture it in your head, you guys. What kind of energy does this car have when it's partway down the hill? This green, smaller, newer car have when it's partway down the hill? Is it moving? Yeah, it's got kinetic energy. It's not at the bottom of the hill, so does it have potential energy? Yes, it would be Q times V. But notice we're also given the value of the final potential, so we don't need to sub in that equation. We could just sub in the value for it, 1.5 times 10 to the negative 8. So far, so good? Well, let's sub in the mass here of the pith ball. We get 3 times 10 to the negative 7 equals 1/2 of 2.4 times 10 to the negative 4 plus 1.5 times 10 to the negative 8. Let's take the 1.5 times 10 to the negative 8 over by subtracting. So we get 3 times 10 to the minus 7, subtract 1.5 times 10 to the minus 8. Gives us 2.85 times 10 to the minus 7. Let's multiply that by 2. Let's divide that by 2.4 times 10 to the minus 4. Finally, what are we going to do with that? We're going to square root it, right? And we get 4.87 or 4.9 times 10 to the minus 2. So we're going to say VF, 4.9 times 10 to the minus 2 meters per second. If you had been given the initial speed of a car, 0 meters per second, the initial potential energy of this car, the final potential energy of this car, you wouldn't have had any trouble in the world finding the final speed of this car. So don't make this question any harder. Just because we can't visualize the charged particle moving quite as much as we can visualize the car moving, don't make it any harder. You treat it the same way. Just replace electric potential energy for gravitational potential energy. Okay, you got it? Perfect timing. Here's your homework questions for the weekend. In addition to your assignment due on Tuesday and your test on Wednesday. I'd like you to do these questions, please, for Monday, sorry. The practice problems on page 571. We will work on page 572 on Monday, so don't panic about that over the weekend. But we'll also assign worksheet number 9 on Monday. So if you want to get a head start on that, you can go ahead and do a couple of those questions. Some of the ones towards the end you might find a little bit more challenging at this point, but if you want to get a bit of a head start, you can do that. It's not homework for Monday, only these 2 questions are. But the rest of it will be will be homework for Tuesday. Okay? That's it. Have a good long weekend, guys, and we'll see everybody on Tuesday, Monday, whatever day.